Now let's talk a little bit more about ANOVA, specifically One-Way ANOVA. ANOVA is a test that allows us to test the null hypothesis that the means of all the populations are equal against the alternative hypothesis that at least one mean vector is not equal. And so below you see that we have set up our null hypothesis and our alternative hypothesis. The null hypothesis being all the means are equal, the alternative hypothesis meaning at least one mean is different. ANOVA is called an omnibus test because it will test for overall differences between the groups, but it will not tell us which one is different. Now some of you might say, well, what good does that do? Well, we have a way of testing that a little bit later. Now, assuming we have a set of data containing test scores from 3 different classes, we're going to use ANOVA to help determine if there is a statistical difference between one of the groups. After we've determined that there is a statistical difference for ANOVA, we will conduct confidence intervals for those groups, as well as conduct some post hoc tests. Now, there are 2 sources of variation that can occur in a sample. Now, let's assume that we have 3 groups, and each group has 10 people, and we're measuring the test scores of individuals under 3 different conditions. We have 10 folks who took an exam in silence, we have 10 folks who took an exam with light jazz music, and we have 10 folks who took an exam with white noise. Within each group, there's going to be some variation that's due to random chance. Then we're going to have some variation that occurs between the groups due to some type of noise or the lack of noise that we've put into this, let's call it an experiment. And we call that the between group variation. So this is the variation that we're going to be measuring with ANOVA. Since there is one variable with 3 levels, we call this a 1-by-3 design. You can consider it as boxes in which you have 1 box, meaning silence, 1 box for light jazz, and 1 box for white noise. Within each box, we actually have the mean for each one of those treatments. So let's look at this graphically. Here we have our 3 groups. We're going to have random variation within each group. And this is caused purely to chance. It assumes that within that group, there was nothing else that was acting on that group that would affect their test scores. The next variation that we're going to look for is we're going to look for the variation between the groups. And the variation is caused by 2 things. First, the variation could be random. We might have a little bit of variance that occurs that's due nothing more to random chance. But since we actually manipulated each group by giving them different sounds, we can consider that as being the primary effect. If there is a difference between the means of these groups, we can assume that the effect that we put in, or the treatment that we put in, this being the silence, the jazz, or the white noise, should have had an effect. So ANOVA determines if the variation between the groups is greater than the variance within the groups. So think about that. If the variance between the groups is greater than what the random chance is within the groups, then it probably means that our treatment or our manipulation, in this case the sound, had an effect on the test scores. And what are we doing here? We're using the ratio of the between group variation over the within group variation. And this will give us an F statistic as well. If there is a difference between the groups, the difference would be much larger in terms of the treatment and random chance than due to random chance by itself. And we will compare this again to an F distribution. Now on the right here, we have an F distribution, and we're going to give it 2 parameters for degrees of freedom as well as a significance level. So in this case, we're going to have a 0.05 significance level, which means we're looking for things in that right triangle or right shaded area, which is the 95% confidence region. If it falls past that, it means that there's probably a difference between the groups, because the between group variation will be greater than the within group variation at a higher ratio. So with setting up our hypothesis test, we obtain the following. Again, we have our null hypothesis where the means are equal. We have our alternative hypothesis where at least one mean is different. When we compute our F value, we compare it to the F critical value from the software, and then we use our rule. If the F calculated is greater than the critical value, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. Since our statistical tools compute p-values as well, it's better for us to do if p-value is less than or equal to alpha, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis, and our significance level is 0.05. So how are the variations computed? What we're going to do is we're going to provide additional notation. So first, we're going to compute an overall or grand mean that we're going to denote as y bar bar, 2 bars above the y. This grand mean gives us the average of the entire data set by itself. In this case, it's 13.73. Now what we're going to do is we're going to compute 2 additional values. We're going to compute this thing called MSB, which is the mean square between the groups, and the MSW, which is the mean square within the groups. We're going to start with the mean square within the groups. The mean square within the groups is basically a sum of squares within the groups divided by the degrees of freedom of the within groups. So I've provided here what each one of the acronyms does. And here is the formula on the right. Now, you can ignore the formula because most of the statistical tools will do this for you. But in case you want to follow through, here we're taking the sum to explain it. For each group that we have, we're taking the sum of the number of observations minus 1 and multiplying it by the variance of that group and then dividing it by the number of observations minus the number of groups. Down below, we've worked this out to have 9 times 13.1, because 13.1 was the variance of the first group, 5.61 the variance of the second group, 3.43 the variance of the third group. When we add these all together, we end up with 113. And we divide by the denominator, n minus g, we had 30 observations minus 3 groups. And we end up with 4.18. Now we're going to take a look at the between group variation. The between group variation examines the variation that occurs between the groups, between group 1, 2, and 3. When we manipulate a variable within a group, we're looking to see if the effect of that manipulation is causing the differences. And that's what this is measuring. The formula here is given as the sum of squares between the groups divided by the degrees of freedom between the groups. Now, the sum of squares between the groups is actually another summation. For each group, we're going to have the total number of observations within the group, and we're going to multiply it by the square of the difference between the mean of the group that we're looking at and the grand mean. And that's why you see there y bar minus y bar bar. That's the mean of the group minus the grand mean. We're going to square it and then multiply it by the number of observations within the group. So within our example, we have MSB is going to be equal to 10, which is the number of observations in group 1. And you can see that for group 1, group 2, group 3. And we're going to multiply by 0.871, which is what we calculated as the y bar minus y bar bar squared. And then for the second group, that same item will be 3.12. And for the third group, it'll be 0.694. And then we divide that by g minus 1, which is the number of groups minus 1. We'll end up with 42.18 divided by 2, which is equal to 23.43. So now that we have that information, we can compute our F statistic. The F statistic is basically the ratio of the mean square between the groups divided by the mean square within groups. It's 23.43 divided by 4.18, which gives a score of 5.59. We can do this with Excel or R or any other application to find that critical value for F that we're going to compare this calculated value of F. And it turns out it's going to be 3.35. Now, remember our hypothesis test. The null hypothesis is that all of the means are equal. The alternative hypothesis is at least one mean is different. Then, using the rules, if the F calculated is greater than or equal to F critical, we will reject the null hypothesis and state that there is evidence that at least one mean is different. So using Excel, the data analysis add-in, it will give us the entire table for the information that we need. Again, we have what we calculated as 5.59, and you can see over here that Excel computed the same value. It provides us with the critical value of 3.35. So here we could do our rules, which says that if the calculated value is greater than or equal to the critical value, we will reject the null hypothesis. Similarly, We can use the p-value directly, as we've done in previous modules, and you can see here that it computes a p-value of 0.00. If the p-value is less than 0.05, we will reject the null hypothesis and state that there is evidence that one being is different.